All right, let's talk next here about this equation, x squared plus 4x minus 3 equals 0. This one does seem to look like we could probably get to solve this one by factoring, but if we try, as we might, x and x for x squared, 3 and 1. Since it's a minus 3, one has to be a positive, one has to be a negative. And for that reason, yeah, there's no way to get the 4 in the middle. So, yeah, this one just doesn't factor. It's not a strong candidate either for the square root method, because if we get the x squared, move these terms to the other side, we'll have an x on that side, and we'll have x's on both sides. That's not good. All right, so, yeah, this one calls for a third technique that we're going to talk about here, and that third technique would be the old quadratic formula. Yeah, it actually can be used to solve any quadratic equation, and some of them, it is the one you have to use pretty much. So let's talk about it. Now, by the quadratic formula, what I mean, it's a set formula, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Maybe you know the song that goes along with it to help you remember it, but Pop Goes the Weasel. But anyway, the solutions can be found this way. Now, what do I mean by a, b, and c? A, b, and c are the coefficients up here. A is the coefficient of your x squared, and since there's not one showing, that's understood there to be a 1, 1x squared. And then b is what's times the x, so b would be 4. And c is the constant, and in this case, that would be negative 3. Take the negative with it. So I'm going to plug those in to various places in this formula. The way I like to think of the first part, the minus b, is it just means the opposite of b. b is 4, so the opposite of b would be negative 4. Then I do plus or minus b squared, so I'm going to square the b, that would be 4 squared. Minus 4 times a, which is 1, times c, which is negative 3. And then divide that by 2 times a, which is 2 times 1. All right? Okay. All right. So then I just simplify all that. And so that's going to get me x equals minus 4 plus or minus square root of 4 squared is 16. Minus 4 times 1 is negative 4, times negative 3 would be positive 12, all divided by 2. So that winds up being negative 4 plus or minus square root of 16 plus 12 is 28, divided by 2, which is a pretty good answer. However, I can simplify. Start by, well, you simplify your square root. 4 times 7 is 28, so I can simplify that. It's negative 4 plus or minus. The square root of 28 is 4 times 7, so I'm going to break that down. Square root of 4 times square root of 7, square root of 28. And then that's all going to be over 2. So I wind up with negative 4 plus or minus square root of 4 is 2, square root of 7 over 2. Okay? Now, since I'm got here things I can reduce by 2, everything but the square root, reduce those by 2, so it'll be negative 2, reduce that by 2, you get 1, reduce that by 2, you get 1, and so you wind up with negative 2 plus or minus 1 square root of 7, you don't have to write that 1, divided by 1, so you don't have to write that 1, so there are the 2 answers. There are 2 answers there. Negative 2 plus the square root of 7 and negative 2 minus the square root of 7. You don't have to split them out there, but just making a point that there are 2 answers there. Okay? All right. yeah, so that sometimes of course, you have to use the quadratic formula. Here is another. How about 2x squared minus 8x plus 11 equals 6. 2x squared minus 8x plus 11 equals 6. Well, one of the things I hadn't pointed out yet, the quadratic formula, like the factoring method, does need one side 0. So I need to make one side 0. I don't have that right here, right now, so I need to do that, get one side to be 0. So I need to subtract the 6 from both sides. So that'll wind up with 2x squared minus 8x plus 5 equals 0. So now I have my a, b, and c. A is 2, b is negative 8, and c is 5 for the quadratic formula, which is x equals minus b, so that's the opposite of b. B is negative 8, so the opposite of b would be positive 8. Then it's plus or minus the square root of b squared, so I square the I am squaring negative 8 minus 4 times a, which is 2, times c, which is 5. And then divide all that by 2a, 2 times 2. So this winds up being 8 plus or minus the square root of negative 8 squared. I am squaring the negative, so that's negative 8 times negative 8. That's positive 64. Minus 4 times 2 is minus 8 times 5 is minus 40. So I'll wind up subtracting 40 here in the square root, and then dividing all by 4, which gets me x equals 8 plus or minus the square root of 24 over 4. Pretty good answer. All I need, though, to do is simplify. So let's do that. Simplify your square root. It's 4 times 6 is 24, so that's going to be 8 plus or minus, and since the square root of 4 is 2, it will be 2 square root of 6 here. All over 4. Okay? All right, so that's pretty good answer, but again, I can simplify. If you look at everything but the square root there, all those reduce by 2. So I'm going to reduce all these by 2. Reduce that by 2, you get 4. 1. Reduce that by 2, you get 2. So here's what I get. I get 4 plus or minus 1 square root of 6. I don't have to write that 1. So just square root of 6 and then divide by 2. And that's the simplified answer. All right? Okay. All right, well, let's also talk about here all right, let me also talk with you here a little bit about linear and quadratic models. Yeah. Of course, what needs to be pointed out is that sometimes, you know, there are data that can be put into an equation format, and some of them will turn out to be linear models, linear equations, and some of them may turn out to be quadratic in type. And so that's what I want to kind of talk with you a little bit about now. And so let's, this refers to the handout, linear and quadratic model handout. And let's talk about number 1. First of all here, it says the number of female participants in high school athletics in millions from 1990 to 1996 can be modeled by the linear equation y equals 0.101t plus 1.844, where 1990, t equals 0 is 1990. That is our model. So they gathered some data up, and it looked to be linear. They could figure out a linear equation that models the data, and this is it. So in other words, if I if I plug in a year, t0 is 1990, t equals 1 would be 1991, so forth and so on, it would give me the number of female participants in millions in high school athletics for that particular year. So, based on that, the A part of number 1 is how many female participants were there in 1995? Okay, well, that information there, what is provided is, of course, the year, which translates to a t value. So this information here, I'm given a t value. T equals 0 is 1990, then 1995 would be t equals what? T equals 5, right? That would be the year t equals 5 in this particular model. So what I'm going to do is I'm going to plug in t, of course, to be 5. That's all I have to do on A here. So I have y equals 101 t, but t we now know is 5, plus 1.844. And yeah, this is a very simple one. Just have to do the math. Multiply by 5, so that would be 0.101 times 5 would be 0.505. Then add in the 1.844. So that would be 2.349 is y, which y is the number of participants in millions. So this is 2.349 million participants in the year 1995. Okay? Easy enough one right there. But let's look at B. B asks a little bit different question. If the linear pattern continues, in which year will there be 3 million participants? Female participants. What is the year in which there will be 3 million participants? All right, so it's based on the same model. Well, there's a couple ways I could do it. We could just keep plugging in years. T equals 5 gives me 2.349. I could do t equals 6. I could keep going that way. However, let's do it a little more direct route, and that is with the given information. If I know I want 3 million participants, isn't that telling me that in my model I want specifically the y to be 3? I want 3 million participants, so wouldn't that tell me y is 3? Yeah, that gives me a value that I'm seeking of y equals 3. So I'm going to plug in this case, instead of giving a t value, they've given me a y value. Y is going to be 3 for 3 million. Well, if I do that, plug that in, the y to be 3 in the model, what that gives me is a little bit more of a challenge, not too bad. I have to solve here for t. It's just solving a linear equation, which we've done so previously. Just get the t value here by itself. So how would I do that? Well, I need to get rid of the 1.844 and the 0.101. And the way I would do that, well, subtract the 1.844, first of all. 3 minus 1.844, both sides. That would be 1.156. And this side would be just 0.101 t now. Divide off then our 0.101 to get the t by itself there, and that gives me here 11.45. Roundabouts. Okay, now, to answer the question though, what year is that? The t, that's 11.45 years, but what year is that? Well, since t equals 0 is 1990, it's 11 years plus a little more. Now, usually, it's 11.45, you'd round, just round it off to 11. But let's look at it this way. This is telling me it's not quite 11 years, it's a little more than 11 years. So wouldn't that mean in the model I would need to go up to 12 years? Yeah. So in 12 years from 1990, I would be reaching 3 million. 11 wouldn't quite get me there. It'd need to be the next year, 12 years, to get me the 3 million. So that would be, what year would that be? Well, it would be 1990 plus the 12, which is 2002. Final answer. Okay? The year would be 2002 when the number would reach 3 million. Okay? All right. Well, let's look at in here number 2 on the handout. This one has from 1970 to 1996 the number of lawyers in thousands in the U.S. modeled by this formula, this equation. L equals 0.139 t squared plus 19.25 t plus 326.5, where in this case t equals 0 is 1970. So L is in thousands. So this gives me the number of lawyers in thousands for year t, which t equals 0 is 1970. All right, so a part of this problem is how many lawyers were there in 1980? That's the question. Part A. Well, if I know the year, then I know, of course, the time, the t. If we're talking 1980, t equals 0.70, wouldn't 1980 be t equals 10? Yeah. So this one is just a matter of plugging in t to be 10. So I have L equals 0.139 times L squared, t squared, plus 19.25 times t, which is 10, plus 326.5. So if I multiply and add all that out, what do I get? That's 0.139 times 100. 10 squared is 100, so that'd be 13.9. 19.25 times 10, that'd be 192.5, and then 326.5. Add that to that. What does that give me? 13.9 plus 192.5 plus 326.5. 532.9. And L is in thousands here. So 532, basically 533,000 lawyers in the year 1980 by this model. All right? Okay, well, let's tackle the last problem there on the handout. B part. According to the quadratic model, in which year would the number of lawyers have reached or surpassed 1 million? So I'm looking for the year which reaches 1 million lawyers. Okay, couple of issues here. First of all, since lawyers in the model is in thousands, let's think about 1 million in terms of thousands. How many thousands is 1 million? Well, if I write 1 million out, 1 with 6 zeros there, here's the thousands part. So isn't 1 million 1,000 thousands? Yeah, 1,000 thousands. So 1 million, we're talking 1,000 lawyers. And so that, for the model, L then would be 1,000. Right? Make sense? All right, so going at this directly then, we could start plugging in t values and see where that takes us. But let's do it the direct way here just to see how we would do that. I'm just going to set L here in the model. L is 1,000. So 1,000 equals that rest of that. 0.139 t squared plus 19.25 t plus 326.5. And what that leaves me is a very nice, lovely quadratic equation that I need to solve. Okay, well, since I've got all these nice decimals, yeah, this factoring is not good. Square root method, no good. This is going to be quadratic formula. So I'm going to use the quadratic formula to get these answers directly here. And to use the quadratic formula, I need one side 0. I don't have that, so I want to do that. Subtract the 1,000 from both sides, and it'll go nicely right here with the 326.5. So 0 then would be on the right, on the left, sorry, 139 t squared, 19.25 t, 326.5 minus 1,000 gives me along about negative 673.5. So there you go for the quadratic formula. A is going to be 0.139, B is going to be 19.25, and C, well, it's going to be negative 673.5. Okay? All right, so let me get me some room here so I can write the rest of this down here. Okay, so this case is going to be t equals minus b, negative 19.25, plus or minus b squared, so it'll be 19.25 squared, minus 4ac, so that'd be minus 4 times 0.139 times c, which is negative 673.5, all over 2a, so that'd be 2 times 0.139. Okay. All right. So yeah, the numbers aren't totally nice, but you can work them out. So it'll be negative 19.25 plus or minus. It'll be 19.25 squared, which is 370.56, roundabout. And then minus 4 times 0.139 times negative 673.5. That gives me positive 374.466. And then we'll divide that by 0.139 times 2, 0.278. All right, so that will get me negative 19.25 plus or minus 370.56 plus 374.466 is 745.026 divided by 0.278. All right, well, I'm seeking a year, a time. This gives me the answer, but it's not entirely clear what year that is. So here's what I'm going to do. I'm going to go ahead and square root that, round that off. So it's negative 19.25 plus or minus the square root of 745.026, 27.29. So say 27.3 divided by 0.278. All right, again, therein is the answer, but it's not entirely clear. Let's divide it up. It's 19.25 plus 27.3 divided by 0.278. And also I've got negative 19.25 minus 27.3 divided by 0.278. Well, yeah, these give me the answers. Now, the only problem with this is this gives me a negative answer, and I don't want a negative answer, so I'm just going to take that one out. Here's the answer. Negative 19.25 plus 27.3 It's 8.05. Then divide that by 0.278, and that'll give me 28.95, which that's close enough there. It's 29. 29 years. So it's going to take 29 years for the lawyers to reach 1 million, and that's in reference to 1970 in this case. So it's the answer would be, so I take the 1970, add 29 years, so that would be 1999 would be that year. Okay?